Okay, today is Wednesday, 9/26, and yesterday we finished completely 1.6, a library of parent functions, and we right at the end talked about absolute values. So if you need to write something about the absolute value function, make sure you do that because it is a parent function. Today we're going to look at transformations of functions. We did not start this yesterday. Our homework checks are listed as 1.5 on Thursday, 1.6 on Friday, 1.7 also on Friday, and of course those are all very soft due dates as we go. So this is 1.7, transformations of functions, and you know, in other math classes, you have looked at transformations of functions, and even I'm going to say in the early years of algebra, without really calling them algebra 1 or linear algebra and intermediate algebra, even without calling them that necessarily. And this is where we move things up, down, left, right, turning, and stretching and compressing and things like that. So transformations of functions. If you can transform one function and you know the parent, you can transform, any function. So we want to use vertical and horizontal shifts to sketch graphs of functions. We want to use reflections to sketch graphs of functions. And we want to use non-rigid transformations to sketch graphs of functions. So we'll start with kind of the vertical and horizontal shifts as we go. So shifting graphs, and this is translating left, right, up, down, and you've done this before in your life. So if I have, either of these problems, here we go. So I have the basic squaring function and the basic cubic function. So if I add 3, we'll say it's going to shift that one up 3. It's going to shift that one up 3. And if that's adding 3 after I've squared it, if I add the 3 inside of the function, it's going to move it left and right. And so I can do the same thing with this or any parent function. So if I'm shifting it up or down, it is what it is. So if I add, it goes up. If I subtract, it goes down. Whoops. And if I shift it left or right, though, it's kind of that opposite thing. So if it's like -2, I'm really shifting it that way too. Or minus, so I'm so sorry, if it's -2, I'm really shifting it that way too. And so it's kind of that opposite thing. So first we'll just look at a picture or two, and then we'll write something. So if we're going to translate up, so this is just that same example, and we'll just start by looking at it, and then we'll maybe write something after we look at it. So here's f of x equals x squared is that kind of gray one. Here's x squared plus 2. It just shifted it up 2. And if we want to shift left or right, though, that's the thing to be careful of. So my hint to you is this. Think about what the 0 or root is there. Do you agree that here's f of x equals x squared? That hits this at 0, right? Hits the x-axis at 0. That's the x-intercept. And this one, if it's x minus 2, it actually hits at positive 2. Remember where we take those factors, x minus 2, set it equal to 0, add 2, so x equals positive 2. So when we're going left or right, it's kind of an opposite action. So if we're saying x minus 2, that might imply that we're going that way, but really we're going this way. And it's actually x minus whatever this is squared. And so it's a subtraction there, and then this is a positive 2. So that's really why we're saying that it's to the right 2 as we go. And that's just kind of seeing it there. And then we want to kind of say something about our vertical shifts and horizontal shifts. So here's the rule thing. And I personally like to draw a little picture by these rules. So let C be a positive real number. Vertical and horizontal shifts in the graph of y equals f of x are represented as follows. If you have f of x plus c, it goes up c units. If you have f of x minus c, it goes down c units. If you're going to move it to the right, it's f of x minus c. If you're going to move it to the left, it's f of x plus c. And I'm going to write the rules next to that. So if you're going down and you're going to need a little space, you might want to, just leave a little space. I'm going to do a little graph on each one of those. And just to let you know, this last one here, I actually, in my head, think of that as x minus negative c, and that helps me remember then that that's going to go left. Whatever will work for you. And like I said, if I can shift one thing, I can shift kind of anything. And we want to know kind of our parent. So if our parent is f of x is x squared, then in this one, if I'm going to add, we'll just add 2 like the book authors did, then h of x here is just x squared plus 2. And so here's my original parabola, and that just moves it up 2. And I'll just change colors so that they're easier to see. And here h of x is x squared minus 2. And then that's going to bring it down to. And so these two first things that are happening, that x squared stays x squared. You're adding 2 outside of that function. And so that's how it looks. It's just a tacked on plus 2 or minus 2. Whereas this one, when we do this one, that means we're replacing x with x minus c. And so in this one, h of x is f of x minus c. And so when we put x minus c here, it's our x minus c, or minus 2. I was going to put it as 2 again. X minus 2 in parentheses squared. So notice that difference is that I'm replacing x here with x minus 2 to do that my left and right kind of things. And so then this one is just going to go to the right 2. And just in your head, if you think about where that 0 is, it would be at positive 2 there. So it's kind of that opposite effect. And then for the horizontal one here, h of x equals parentheses x plus 2 in parentheses squared. So this changes x to x plus or minus. This changed not the rule, but just tacked on an extra, plus or minus or whatever it happens to be. Oops, I kind of missed the point there. And so that went to the left. So we want to be able to identify the rule and then what's happening there. So I just picked x squared. The absolute value of x would look very like that, right? Because it's the 2 linear things, and it just goes up, down, left, right. And x to the third, 1 over x, the same thing happens. So think about if you could see what these would be. If this was 1 over x, and I'm just going to write these in yellow. So if this was 1 over x, which kind of looks like that, right? And then if this is 1 over x plus 2, we'll say, then it's going to shift everything up so that one asymptote goes up to 2 a little bit, and then it kind of looks like this. And I'm not going to do the subtracting one, it would just move it down. But then this one would be 1 over x minus 2 like that. Do you see that x is going to change into x minus 2? And then that's going to move it to the right. So this graph would be have my asymptote over there, and then this one is like that and like that. Okay, so if you can do it kind of with one function, parent function, you can do it with any parent function. And I'm going to erase all that, but there we go. But if you can do it with one function, you can do it with any. And then the other thing is, can I look at the rule and know what has happened here? And so that's what we're going to look at in this next one. There it is. So it says use the graph of x to the f of x equals x to the third to sketch the graph of each function. And so I'm going to do that on some graph paper, and you decide if you are going to do it on graph paper or just, yeah, not. Ooh, I don't know why that didn't look there. I don't know, I didn't like that first one. There we go. And I just think, you know, if I have it on graph paper, then I'm truly going to be able to know what I'm looking at. So it says use the graph of f of x equals x to the third. So I'll graph that and in green every time. So x to the third, I want to be able to give good points. So it's at 0, 0. 1 to the third is 1. 2 to the third is 8. So that goes, oh, yeah, 2 to the third is 8. That goes all the way up to 8 here. And then for my negative ones, at negative 1 to the third is negative 8. Negative 2 to the third is negative 8. And my board needs to be oriented. Maybe I'll just do that right now. Or maybe I won't. Oh, there we go. Oh, okay. Oh, that's a pretty sound. Okay, so then here's my original graph. And so for both of these, I think start out as x to the third. And so while I'm at it, I'm going to draw the graph for b as well. And at 2, 1, 2, 3, 4, 5, 6, 7, 8, and 2, negative 8. Oh, darn, I was doing great until I curved in. I don't know. Well, anyway, that's why we put a couple dots there. So we're good to go. So what happens with g of x in letter A? Somebody tell me. We must know. It goes down 1. And so the easy way to do that graphically, g of x is x to the third minus 1. I'm going to slide that down so I can kind of just see it a little bit easier. And so then I can just easily move all of my key points down 1, and then I will just have it. It gets a little tricky, you know, with these kind of almost straight lines to kind of think about or see where that's going to be as it goes, but we'll do the best we can. Ooh. Okay, yeah, the best we can sometimes isn't great. And so this one translates down 1. And on quiz tests, I do accept it. it shifts -1, or oh no, I think for that you are going to want to say down, up or down, because that shifts -1. Am I going left or right or up or down? Does that make sense? As I speak it, then it reminds me that I want to say that. So I want to go down 1 for that one. And then for this one, I think 2 things are happening. What's happening here from that part? It goes up 1, and what happens here? To the left 2, left 2. And I think of that as minus a negative. And so this h of x is x plus 2 to the 3rd plus 1. And then to be super honest, that's why if I plotted those points, it's very easy for me to graph that new graph. Oh, I did. I just noticed I forgot the 2, and that's bad because now it's not going to move all together. But that's all right. So I can, and does it matter if I go up 1 and then left 2, or left 2 and then up 1? No, that's not going to make a difference. And sometimes based on how things are written, things like that can make a difference. So I'll do this one up 1 and left 2, and this one will go up 1 and left 2. This one will go up 1 and left 2. This one, which I didn't do a dot for, will go up 1 and left 2. And then my way down here one will go up 1 and left 2. And truly, what I should be able to do, and let's see if I can, I should be able to clone that because I didn't change the shape of it. I should be able to change it to blue and then just push it into place at the smartboard at least, right? So I can't do that on pencil and paper, but there's what's happening, and then I just want to state what happened. This is a translation, translates, and shifts or moves. Those are all words that I accept, and up 1 and that's and left 2. And if you can do x to the 3rd, you can do 1 over x, the square root of x, anything, right? So if I had, you know, and I'll just pretend for a minute, I'll do if f of x was the square root of x, that looks like this, 1, 2, 3, 4, like that. And then if I moved it down 1, it would just be there. And if I did that other one, it would be, let me go back. There we go. And if I did that other thing, oh, never mind. I'm just gonna not move it all together. And then it would have been what? Up 1 and left 2, so it would kind of move it like that. So if I can do one parent function, I can do every parent function as we go, and looking at what happens. The key is being able to look at that rule and then see what happens. Then reflecting is the next thing. And so reflecting graphs. Generally, we reflect in the x-axis because if we reflect in the y-axis, sometimes that's just not as interesting, like x squared. If you reflect it in the y-axis, like, you know, ooh. there's not as much happening there, but it can be either. I shouldn't just say that. As we go. So reflecting graphs. So this is just that little introduction. It's that mirror image. If f of x is x squared, that like light gray one, and h of x is negative x squared, it is the mirror image or reflection in the x-axis there. And so here's kind of our rules. So reflections in the coordinate axes. Reflections in the coordinate axes of the graph y equals f of x are represented as follows. So the reflection in the x-axis is h of x equals negative f of x. And by the way, notice that negative is like outside of the function. And whereas if we reflect it in the y-axis, that negative is inside that x. So we change the x. that's why if we had x squared and we put in a negative x, it's still x squared. And so that's why we don't always do it, quite like that. So then our next one is going to be, can you see a picture of the graph and figure out what the rule is? And so the first couple problems, we had the rule and we want to graph it, and we want to be able to go back and forth for any of these. Do you still need to see these? Yes or no? Okay, x-axis and y-axis. So here's this next one, and it's kind of written a little funny. So you might want to just. It takes me a couple slides to do this. So I'm actually going to write what they have here on the next slide. So x to the fourth can be considered a parent function even. It's that parabolic shape. It's a little flatter here seeming and then shooting quickly up as we go. But that's what it looks like, and that's our f of x. So I would ask that you try to sketch these. That's not always super easy, but let's just sketch that. This is number 2, f of x is x to the fourth. And, on your paper, you're just making kind of a flat looking, at the bottom, parabola looking thing. So x to the fourth. And then on these, it's a little hard to exactly show what's happening, but I'll just do it freehand like this as well, so that we can kind of see it. Do you notice, obviously it's reflected, but it's also shifted like it looks like up 2, correct? Does that seem right? That it's, because this says 3, so 1, 2. So I would make maybe a couple little marks, 1, 2, and I would just put that kind of flat looking thing like that. And then we have it there. And then likewise for this one, it's flipped again, and it looks like 1, 2, 3 out that way. So I'll go 1, 2, 3. So they're doing kind of the new thing and what the old things were. And that just kind of flat or parabola, a little hard for me to quite write in there. So I would say you're just kind of sketching those so that you can see them. And I would make sure that I know that that's the number 2 right there and that that's the number 3 right there if you're doing it freehand. And then I'll write these over here. So it says each of the graphs below is a transformation of the graph of f, which we know was x to the fourth, and write an equation for each of these functions. So think about what your rule is going to be for these, and maybe you've written it or you know what it is or whatever. Do we agree that all of them are reflected in the x-axis, right? And so because they're, excuse me, reflected in the x-axis, the negative would be out in front there, right? And think about the difference. And I'll just do this x to the fourth again really quick here, and these three. So if that's x to the fourth, it looks like this. If I have f of negative x, that would be negative x to the fourth, which a negative, negative, negative is positive. So that would be the same, oh, fourth. And then if I have negative f of x, then that's negative outside x to the fourth. And then that's what reflects it in that x-axis. And again, we don't have that graphing calculator to kind of help us as we go. So I have this little yellow one. If I flip it up and down, and it doesn't flip it the way we would expect. So there it is flipped upside down. And then how do I move it? What do I have to do? Up 2, right? So where does that plus 2 go? Does it go inside there or outside? Outside. And so for this one, and I'll just move that a minute, for letter A, and I'll just write it here, g of x is what they're calling this one. G of x is the negative out in front of x to the fourth, but then plus 2 kind of to move it up 2. So, and we'll write kind of the two things too. It's reflected in the x-axis, and it's shifted up 2. Shifted up 2. Does it matter what order you do that in? Could you shift it up 2 and flip it and get the same thing? Yes. So in that case, you could. And then the other one here, I'll write maybe in purple because I haven't used purple, is h of x. And we already said that we flipped that one again. So if I'm back here, I flip that, but then I'm moving over that way. And so when I do that, what am I doing with 3? What am I going to do with 3? Add or subtract it? It's going to be minus 3 to move it to the right. And where's the minus 3 going to go? On the outside or inside? Inside. And to me, inside means it's going to go in there. In place of x, it's going to be x minus 3. And so this is, the negative is outside. That flips it in the x-axis. And then x minus 3 in parentheses. Oh, not squared. I don't know. For some reason, squared always is in my head, maybe. I don't know. To the fourth. And so this is reflected in the x-axis and shifted to the right 3. So kind of, you know, an example of the two things that are happening. The reflections were both in the x-axis, so the negative is outside of there. And then if we're moving up or down, it is what it is and it's outside, so just plus 2. If we're moving left or right, it's within that x value of the rule, and then we're moving left, right. Did I say up, down for 2? I don't know. In my head, I wasn't sure. Okay, so then the next thing I want to do is look at the square root of x, because do you agree here the domain is all real numbers? And for the square root of x, the domain isn't all real numbers. And so we maybe have to kind of think about that a little bit as we go. And so this is all there. And okay, and let's see, I'll just read this. When sketching the graphs of functions involving square roots, remember you must restrict the domain to exclude negative values inside of the radical. And we're actually going to do these as a little series of problems. And so we're going to start with the square root of x, which will be f of x. And so this is going to be example 3. You don't have to write any of that because we're gonna do that all those problems. And so the first thing we're going to do is we're going to say f of x is the square root of x, and we'll just do our little sketch of that. 0, 0, 1, 1, 4, 2. I should have not drawn the dots because I can't do it that way. X. I'm going to have to just do it like this. And then I'll put the dots on there. So there's f of x equals the square root of x. And remember our domain or our x values, x has to be greater than or equal to 0, because if it has to be, whatever's under the radical has to be greater than or equal to 0. So letter A is g of x, which is the negative square root of x. That's going to reflect it where? In what axis? The x-axis. It's outside of the rule, so it's going to reflect it in the x-axis. And so when I reflect that in the x-axis, it's just going to go like that. So I've got 0, 0 there, 1, 1, negative 1, and then 4, negative 2. And does that make sense? Because if I put 4 in there, it's the negative square root of 4. And so when in doubt, plot it out. That's my cue to you. You could always make a table of values. Remember me saying that early on, that you're thinking, why would I ever make a table of values? It's a waste of my time. No, it isn't, especially if you're not always going to be, 100% sure of what happened. So this reflected in the x-axis, reflect in the x-axis. What's the domain this time? Same thing, right? So x is greater than or equal to 0. So the same domain for that one as we go. Letter B is going to be h of x, which is the square root of negative x. And so right away you might be thinking, ooh, these are non-real answers. Well, they're non-real answers if I put in positive values of x, but now if I put in negative values of x, a negative negative will be positive, so it'll work out. And so what is that going to do to this graph? It reflects it in the y-axis. And so I'm going to write that, reflect in the y-axis. And again, if I'm unsure, I can always plot a bunch of points. And so it's that original, it's 0, it's 0. At negative 1, it'll be 1. For some reason, I can't do the points always. And then at negative 4, it'll be 2 as we go through there. And so now, when we figure out our domain, this time it's going to be this. Negative x, because it's what's under the radical, has to be greater than or equal to 0. So when I divide by negative 1, what do I do with that inequality? I flip it. So that means positive x has to be greater or less than or equal to 0. So there's our domain for that one, just to let you see. And if you're unsure of how you're getting these domains, you just take whatever's under the radical, set that greater than or equal to 0, and solve for or get x alone. And so then the next one is k of x, and k of x is negative square root of x plus 2. And so think about where that plus 2 of x is, and this negative does what to it? What does reflects in the x-axis? What does that plus 2 do? It moves it to the left. I'm sorry, when I'm in front of you, I'm like, I don't know. It moves it to the left too. So this is going to be reflected in the x-axis and shifts left 2. So if I graph it, it's kind of almost easier for me to kind of see what's happening there. So here, in my head, there's the original, then I reflect it, it's going to go kind of like this, and then I'm going to move it to the left 2, so it's kind of going to look like that. So there was my like 0, 0 point, my 0, 1 point, and my 4, 2 point. I can find kind of where they are. But notice my domain now is really going to start there. So to figure out my domain, I'm going to take that and say x plus 2 has to be greater than or equal to 0. Add 2, x has to be greater than or equal to negative 2. And visually I can see that as long as I'm graphing it, but sometimes, I won't have all of that with me. Then non-rigid transformations in Janet Jones's world are sometimes hard to communicate effectively, but because of the words stretching and shrinking and the way they kind of look there on the axis. So this is our non-rigid transformations. So all the left, right, up, down stuff, just the shape stays the same. We just move it all around. Now we're going to stretch or shrink it vertically or horizontally. And one of the reasons this is a little harder to communicate is because visually the opposite things can kind of look the same. If I stretch it horizontally or I shrink it vertically, it might look the same in practice. But the rules are a little different. So rigid transformations means it's like I could pick up that function and then just move it around or flip it. That's all rigid. Non-rigid means then I'm kind of doing all this kind of stuff as I go there. And let me just see what kind of slide I have there. Okay, so rigid are all these horizontal, vertical, and reflections are rigid. Non-rigid are things that distort the picture. And I can do that on the smart board. So rigid is, oh, there it is, and non-rigid is like I have to break that like little. So sometimes I can do it, sometimes I can't. I can't. I can't. Oh. Yeah. And of course, when I don't want it to break in geometry, then it breaks, So, okay, forget that that didn't do me any good. Let's just get rid of it. But non-rigid transformations are the ones that do some kind of cause a distortion. Rigid transformations, horizontal shifts, vertical shifts, and all that good stuff. So, and if you can do one parent, you can do all the parents as we go. So for this one, for instance, a non-rigid transformation of the graph of this is that where the transformation is a vertical stretch. So this one, they had them nicely laid out in the other ones, but this one doesn't do that. This is your kind of thing. So if f of x was your original and g of x is c times f of x, then if c is greater than 1, C is greater than 1, it's a vertical stretch. Vertical stretch. And if C is between 0 and 1, so if it's negative, it's a flip and stretch, right? But if it's between 0 and 1, so it's a fraction, a half, a third, 5/8 or something. So if it's 0 is less than C, which is less than 1, it's called a vertical shrink. Vertical shrink. So for instance, if f of x is, I'll just do x squared. Yeah, this will be easier, just easy enough to see. But x squared looks like this. Just pretend with me. So then if this is, and And think about what I'm saying here. This is the 2 on the outside, so maybe it's like 2x squared. Then do you agree it becomes narrower? So it looks like that. And does that make sense to you? Vertically, it's stretching. It's like pulling it that way. And then if this is like 1/4 x squared, then it's going to be bullier. Oh, out like that. So that's a vertical shrink. And does that make sense because it's smushing it down? It's always the horizontal ones that seem kind of the opposite. And you're going to also see that, you know, it's not as easy to kind of follow these. So look at where the C is now, right? Here the C was outside. Now it's in the rule. And so, oh, I didn't, okay, vertical stretch. Okay, I didn't write it exactly that way. So then if h of x is f of cx, where I put that number I'm multiplying by in the rule, then if c is greater than 1, it's called a horizontal shrink. Horizontal shrink. And when c is between 0 and 1, it's a horizontal, I'm not going to write that word out again, stretch. And I know I'm kind of way down here on the board, but I want to kind of use the same thing, and I'm going to show you why this is a little trickier. Because now, suppose I'll just stay with that x squared a minute, and so suppose instead of having the 2 outside there, I put the 2 in here, so it would be 2x squared. Well, I can actually get that 2 to come out, right? And 4x squared. So when the 2 comes out as a 4, it could look like this, right? So it's still going to go like that, thinner, but this time so I think in our minds it's easy to think of it stretching vertically like that, but now it's actually horizontally shrinking it. So it's actually pushing it horizontally together is the best I can say. And same thing here. If I have 1/4 x squared, that's like 1/8 x squared if I pull it out, and then I would say it like that. But it's going to be that bowly shape. And I'm now saying that it's stretching it horizontally. It's kind of pulling it that way horizontally. So in my mind, those are hard to convey in words, I feel like. So you just kind of have to look at what it's doing, because it is, you know, you can make that look like these. So it's all how it kind of starts out that you want to kind of say that what is happening there. And if you can do 1, you can do 100. Oh, just kidding. I won't, or well, maybe you will do 100. Does anybody need to see this? And I feel like in the other ones, they wrote it out really nice for you, and then they just kind of put it all here. So here's our next one. This is number 4. And so I'm going to use this whole board and say f of x is the absolute value of x. And I think I do want to graph these on graph paper. An absolute value is a lot like, oh, I used to have a like littler graph paper. Okay, well, ooh, there we go. There we go. I used to have a littler graph paper, but I'll just use this big, huge one. That's all right. So f of x is the absolute value of x, so we can plot some points 0, 0, 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, negative 3, 3. And here's my absolute value graph. There's my original. And so then for part A, and I'll put that down lower. For part A, we want, and of course we can have more than one transformation. Let me undo that. I must have done too much there. And so for letter A, we have h of x. I should just put them right on here. I will. And for letter B, we'll have g of x. Okay. And I'll just plot that original in green again. And so the little thing about absolute value is you do want to think about where that bottom point is. That did not work out well for me that time. There we go. Okay. And so there's the original. So what is going to happen for h of x? H of x is 3, the absolute value of x. How would you state what's happening there? Vertical or horizontal? And stretch or shrink? Vertical, stretch. It's outside of here, so it's vertical. And it's bigger than 1, so it's a stretch. And this time it's really by a factor of 3. And then when in doubt, plot it out. So I'm just 0 times 3 is 0. 1 times 3 is 3. 2 times 3 is 6. And I'll just reflect those over here as well. And then here's my new picture for those. And I'm going to tell you, if you want to do well on this, you've got to practice physically just graphing these and physically writing these rules when you see the graphs. And it's not earth-shattering news, and it's things you've done before, but if you don't practice it, it really is going to be hard for you to be able to do it outside of the having things to look at when you're testing. So this one, is it vertical or horizontal? It's considered vertical again, vertical. And is it a stretch or a shrink? It's a shrink by a factor of 1/3. And so this one's a little harder to maybe plot. So I'm going to go to 3. When it's 3, 1/3, it'll be 1. When it's 6, 1, 2, 3, 4, 5, 6, 1/3 of that is 2. And that just gives me some easy points to go by. 3 that way. 3, 6, I think I'm there. And now, here's my next question. Could you have these exact same graphs and have them be the opposite, these exact same graphs and have different rules and consider them the opposite? So really, just a note to self, if this had been a FHG J of x is the absolute value of 1/3 x. Now, is that the exact same as the red graph, right? Same graph as red. Graph as red. Oh, but what would you say about it? It's a horizontal stretch. Okay, and I'm going to add that in, but it is horizontal stretch. Okay. We will have to finish this one tomorrow. My apologies for going right to the end. I lost a little track there. You too.